share the slides. Yes. Yes. Anybody confirm I'm audible and the slides can be seen?
Yes.
Yes.
Thank you. Thank you. All right. So we studied different type of latches and flip-flops. Latches are label triggered in the sense that when the input changes, the output can also transition. And if you have a enable additional gates, which so that the latch is enabled by a clock, then it's called a clocked latch or a synchronous latch or a flip-flop. So there are we studied different type of flip-flops. The simplest is the SR flip-flop, which is if S is, it has two inputs, S and R. If S is 0, R is 0, the state is unchanged. If S is 1, state is 1. If R is 1, state is 0. And if both S and R are 1, it's an undefined state. Similarly, we had the JK flip-flop, which is same as the SR flip-flop with the 1 is J and K being 1 also in valid state. So if J is 0, K is 0, the output is unchanged. The state is unchanged. If J is 1, K is 0, it's set to 1. State is set to 1. If J is 0, K is 1, state is set to 0. If J is 1, K is 1, the state flips. It complements. Similarly, you have the D flip-flop, which is kind of, if you take the SR flip-flop and if you set both S and R to, if you set both S and R to, if you connect them by a gate circuit, what you get in the D flip-flop is that whatever is the input T, in the next QT plus 1, whatever be QT, it will be the D itself. So QT is equal to DT. QT plus 1 equal to DT. Similarly, you have the toggle flip-flop, which again can be obtained by connecting the two inputs of a JK flip-flop. And there, if the input is, say, T, in the QT plus 1 is the toggle of QT. So QT plus 1 is QT bar. So these are the 4 flip-flops that we have. And again, each of these flip-flops can be either label triggered or they can be clock triggered in 2 ways. One is it is an on clock trigger. Whenever the clock is on, this is enabled. It is activated, or it can be edge clock triggered. That means either at the leading edge, the up edge of the clock, it can make a change. It waits for the next up edge of the clock and only then it makes a change. Whereas if the if in a label control, it's immediately whenever the input comes. And you can also have the negative edge triggered flip-flop, where on the down edge there is a transition. We also seen that this can be implemented using a kind of edge detection circuit consisting of 3 latches, a differential kind of latch. And also sometimes instead of edge triggered, you can have a master slave combination, which makes the transition in a small window of time when the clock changes, only in that time, not exactly edge, but in a small window of time, following the edge or leading the edge. So these are the basic elements. These are basic circuit elements, and also we have seen that any of these 4 flip-flop types can be converted to another one by a suitable combinatorial circuit, combinational circuit. It can be easily converted by adding additional gates. So today what we'll see is that so see, if we review whatever we have studied in the course so far, not only from a theoretical point of view of the Boolean algebra and the finite state machine, in terms of the circuit elements that we have studied, you can remember we studied a lot of arithmetic operations like adder, subtractor, getting the binary representation, BCD representation. In fact, we didn't study multiplier, but it's also easy to build a multiplier. Then we studied some of the some of the so these we would call as the arithmetic operations that you can have using simple logic circuits. Then using these flip-flops of memory elements, you got registers, you got shift registers, which is nothing but an array of flip-flops, a collection of flip-flops, and these acts as your memory. This acts as your memory. So this arithmetic unit, in fact, arithmetic unit can be extended a bit further to have what is called a comparator. You would say if one value is greater than the other. So, and then you can do logical operations. You can find the end of 2-bit vectors. So you get arithmetic and logic operations available, and then you have these registers or memory operations available. And these two circuits combined is all you need to build a CPU. These two circuits combined is all you need to build a CPU. Okay, so there is one more important component of the CPU is that because it is a synchronous circuit, it can things happen only at the clock. You also need something to count or kind of keep a track of how the operations as they get on performed. Okay, so you also need a counter. You also need a counter. In fact, there will be a more general form of a counter, which you would call as a controller, which will control the if-then-else structure, which will control which information, which instruction to process, which operation, addition or multiplication or comparison, what to process under some output of some logical function. So you need program controllers. You need controllers. And these counters, controllers, arithmetic logic units, register, they would together be everything that is inside a CPU. And so these are enough. The early CPUs, the earliest CPUs in the 1960s and 70s had only these elements. Of course, the modern CPUs will have many of them, not just one, they will have many of them, and they will do additional sophistications so that you can do faster computation. But the basic, if you don't bother about the time, how much time it takes to perform certain operation, the basic operations are all these you need. These are the only digital circuits that you need to build a CPU. Okay, so arithmetic logic units you have completed, basic memory and finite state machines you have completed. We'll cover two more important elements. As I said, one is a counter, and register we have little bit covered, but some more details we'll cover in the next class. All right, so let's carry out our discussion on counters. All right, so a counter is nothing but a circuit which provides an output that counts the number of time a particular event has happened. As the name suggests, it keeps an count of the number of time an event has occurred. How does it do it? It does it in terms of a sequential circuit, a finite state machine, and to each of the value of the count, say 1, 2, 3, 4, or whatever, each of the value of the count, it has a state of the circuit associated with it. So there is a one-to-one mapping between a count value and a circuit state. Okay, and then what happens is that whenever an event happens, the circuit transitions from one state to another. And since there is a one-to-one correspondence between a circuit state and a count value, just by looking at what state the circuit is in, we can find out the count value. So if we look at the now what this event can be, this event actually can be anything. It can be anything. It can be maybe how many people has come inside a room. It can be how many times a motor has rotated. It can be in the most common form that we will use will be this will be how many clock edges you have encountered, you have got as input. So all our discussion we'll see, because all the other these external events and other things, they can be converted into a train of pulses. They can be converted into train of pulses, which we call as a clock. So without loss of generality, we'll say that our events will be nothing but clock cycles. So all the counters we design will count how many clock cycles has happened. Okay, so and the count value will go up 0, 1, 2, 3, 4. So if we have k states, we can count up to k. So this is called a modulo k or a mod k counter. It counts up to k. It can count k distinct values, k distinct count values. So we'll see that it's natural, because if you have n flip-flops, you can have at most 2 to the power n possible states. So if you want to count up to k, your 2 to the power n should be greater than equal to k. 2 to the power n should be greater than equal to k. So if you want to have a, say, if you want to count till 14, you have to take 2 to the power 4. You need 16 states. Okay, so if we look at and there is a repeatability. So if we look at the state transition diagram, it's kind of a simple and circular state transition diagram. There is no branching kind of thing. So one count, it's the property of any arithmetic. Is the, if we increase the count plus I plus is, you can have only one value, next you can have two values. So it's a simple cyclical state transition diagram where you move towards the count. And the thing is that after you reach the highest count, then it resets to the first count. It resets to the first count, which may be 0, which may be 1, as we decide, as we have our convention. So it resets and then it cycles. Now this cycling, even though the basic diagram is of this type, these cyclings can be both directional. It can be an up count, and also it can be a down count. It can be either a up count or a down count. So in general, so the mapping of the states to the count values, in general, they can be more complex. So in general, you may need a decoder circuit, or which is basically a combinational gate circuit, decoder circuit, which converts a state. Maybe now the state in the native form, this can be represented by the flip-flop value. So if you have 3 flip-flops, a state can be, say, 0, 0, 0, means all 3 flip-flops are in 0 state, or 0, 1, 0, so 0, 1 and 0 is the flip-flop steps. Now the output count values need not be 0, 1, 0 and 0, 0, 0 and so on. They can be in general. They can be something. They can be a, say, display. There can be a display like this 7-segment LED display. They can be anything. So in general, you will need a decoder to convert this by state representation to the desired output. But it can always be done because there is a one-to-one mapping between the state and the desired output value. Okay, so also again, without loss of generality, initially we will consider a direct mapping of the state to the output. So there is no decoder. The decoder is kind of an identity function. Okay, so if the state is in the second state, the output will be if the decoder is in 0, 1, 0 state, the output will be 2. The count will be 2. So this is called a binary counter. Binary means the states, the flip-flop values, the flip-flop state values are nothing but binary representation of the count number. So if the count number is 3, 0, 1, 1 is the state. So this is called a binary counter because it's the binary representation. In general, we can have other counters which will require a decoder between the flip-flop states and the desired output. A typical example is a digital clock where you have the display as 7-segment displays. BCD kind of converter will be required. Okay, so this is what is a counter. Now let us try to design initially. Let us try again this. Okay, let us try to design these counters using flip-flops. All right. So now again, I'll just explain how do you go about this design process. But again, let me tell, there are again two type of counter. One is called a asynchronous counter, which means that, see, let's say I want to count from 0 to 7. I want a up counter which is mod 8. That means I want to count 0 and then 1 and then up to 7 and then back to 0. Okay, then back to 0. So if we, so it's a mod 8, so I'll need 3 flip-flops. Let's call them Q1, Q2, and Q3. So the corresponding binary values will be 0, 0, 0, 0, 0, 1, 0, 1, 0, and so on up to 1, 1, 1, and then back again. All right, so this is a mod 8 up counter. And I will need, since it's mod 8, I'll need 3 flip-flops to design this up counter. All right, now how this transition happens between these values, this again can be of two types. One is asynchronous. Because you see that when you change from one state to another state, potentially all these Q1, Q2, Q3 values can change. So this will change to this will change to this, and this will change to this. All these 3 values can change. Okay, when you transition from one state to another state. In the asynchronous counter, what happens is that all these 3 changes or k changes, if you have a k bit, need not occur in the same clock cycle, same clock edge, need not occur in the same clock edge. So the first bit, the least significant bit, may change in one clock cycle, the second most least significant bit should change in the next cycle, and so on. All these 3 changes need not happen in the same clock cycle. Okay, so just maybe one bit changes and another bit changes. Of course, this may lead to some problems. This may be problematic. This will take more time. For example, if only one bit can change in one cycle, then to move from 0, 0, 0 to 0, 1, 1, if all of this only one bit can change in one clock cycle, I'll need 2 clock cycles to make this transition. Okay, so it needs more time, but the advantage is that we'll see that the circuit we need to implement this is much simpler. On the other hand, we have the synchronous counters. Synchronous counter, where all 3 bits can change, will change in the same clock edge. Will change in the same clock edge, right? So this the advantage again is that it's fast. In just single clock cycle, you can move from 0, 0, 0 to 0, 1, 1. Okay, but the drawback again is that there's a trade-off. That means you will need more gates, you will need more circuits. So see, all of these digital electronics, there is always a trade-off. There's a space-time kind of trade-off. If you want to do things fast in less number of clock cycles, you will need more circuit. You will need more area in your integrated IC, in your VLSI IC. You will need more area, more transistors to implement the circuit. And if you want to do it in less area, you will need more clock cycles. You will need more clock cycles to do it. Okay, so there is always this trade-off, and depending on your application, which side of the trade-off you go, that is determined. Okay, so let's start with the asynchronous counter. Okay, let's start with the asynchronous counter. We will first study a simple asynchronous counter called a ripple counter. Ripple counter. Okay, so what the ripple counter will do is something like this. Suppose I start with this. Then, so let's say this is my LSB and this is my MSB. So what will happen is that in the clock cycle 1, only the LSB will change if required. LSB will change only in the clock cycle 1. So you will get this. And in the next clock cycle, the next bit will change. So we'll get this. And in the third clock cycle, the next bit will change. If required, they may not change also. I'm just writing out. Maybe they will remain the same. And maybe they will remain the same. But if there is a change, it will happen only in the third clock cycle. So as if this change, these bits that are changing, ripples from MSB to NSB, just like you saw in a ripple carry adder. Okay, so first the least significant bit is added, then its carry is gone to the next significant bit, then to the next significant bit, and so on. So this way also, first bit changes, in the next cycle, next bit changes, in the next cycle, next bit changes, and so on. Okay, so as if you look at a clock kind of thing or a counter kind of thing in a time snapshot, if you look, you will see only one position changing at a time. You will see only one position changing at a time at each clock cycle. Whereas as a synchronous, all three will change at a time. All three will change at a time. Okay, so but this is called a ripple counter. So we'll see that we'll try to build a circuit to implement this ripple counter. Implement this ripple counter. Let me insert. Let me do one thing. Yes. Okay. So how do we design? Let us look at this observation. Let's have a mod 8 counter. Okay, so let us look at the values. So 0, 0, 0 is 1. 0, 0, 1 is 2. We have it's a binary counter, so no decoder is required. Let me write down the whole thing. Have I made a mistake? Oh, sorry. Seven. Okay, so if it is a binary counter, if my flip-flops go through these values and I do a binary to decimal counter conversion, then my output will look like 0, 1, 2, 3, 4, 5, 6, 7. It will look like this. Okay, and then again back to 0. It will look like this. Okay, notice one pattern. Notice one pattern. If we look at the least significant bit, whenever the least significant bit goes from 1 to 0, only then the next significant bit makes a transition. So let's find out the 1 to 0s. This is a 1 to 0 transition. This is a 1 to 0 transition. This is a 1 to 0 transition. You see that this has flipped. Here this has flipped. Here this has flipped. Here this has flipped. Okay, so if I call these as Q2, Q1, Q0, so Q1 toggles when Q0 is going from 1 to 0. Okay, Q1 toggles when Q0 goes from 1 to 0. That means if Q1 was a toggle flip-flop, if Q1 was a toggle flip-flop, if Q1 was a toggle flip-flop and you have a clock on the falling edge of the clock, if we added Q0 in the falling edge of the clock, if we added Q0, then this would be satisfied. That means when Q0 goes from 1, you know what a toggle flip-flop does? So this is a toggle flip-flop. So what a toggle flip-flop does is whenever t is 1, Q goes to Qt plus 1 is Q bar, Qt plus. So it toggles the output, right? And this happens at the edge of the clock. So if you have a negative edge triggered clock, what will happen is if this t is permanently set to 1, if t is permanently set to 1, at all the negative edges of the clock, this will toggle. But when do I want Q1 to toggle? I want Q1 to toggle only when Q1 has a negative edge. If Q0 was a clock, if it have a negative edge. So do one thing, make Q0 the clock of Q1, make Q0 the clock of Q1, a negative edge clock, low activated clock, a negative edge clock, and then this you permanently set to logical 1. Okay, so VDD or something, this you permanently set to logical 1. And whenever this clock comes, Q0 comes, you make 2. Note that this operation repeats. If you look at Q1, whenever Q1 goes from 1 to 0, only then Q2 makes a transition. Q2 makes a toggle. Okay, so let's see when does Q1 goes to 1 to 0. This is where it goes to 1 to 0. This is where it goes to 1 to 0. Only 2 places. You see, these are the only 2 places where Q1 toggles. Q1 toggles. Okay, so if I have a circuit like this, as follows. So note that I am writing the flip-flops in the reverse order. So this is my, say, TFF1, toggle flip-flop 1, and this is my TFF2, and this is my TFF3, and this is my Q0. I'm not drawing the bar 1. This is my Q1, and this is my Q2. Note that I am LSB I am writing in the left. And what I do is that this toggle of each of these, say T0, T1, T2, all of them I tie to 1. All of them I tie to logical 1, plus 5 volt or something. Okay, and the clock, which is a negative edge triggered clock, the first one I give the normal clock. The first flip-flop I give the 0th flip-flop I give the normal clock. The output of the first flip-flop is the clock for the second flip-flop, negative edge clock of the output of the second flip-flop is the negative edge clock for the third flip-flop. And these are my observed states, Q0, Q1, Q2. Okay, got it. So whenever Q0 goes down, Q1 makes a toggle. Whenever Q1 goes down, because it's a clock for Q2, Q2 goes down. Okay, so this is a kind and the first Q0, that is for the first flip-flop T0, the TFF1, that clock is the normal clock. Okay, so you can see it's as if there's a ripple. So first Q0 is changing, then Q1 is changing, then Q2 is changing. It's the ripple. And if you observe Q0, Q1, Q2, they will be in the same order as we mentioned, 0, 0, 0, 0, 0, 1, 0, 1, 0, and so on, because of the toggle property of the toggle flip-flop. It will toggle like that. Okay, any doubt? All right. So now this was an up counter. What can I do to design a down counter? What can I do to design a down counter? You will observe that the rule is reversed. So now here I say when Q0 goes from 1 to 0, Q1 makes a toggle. The down counter, if we write down the sequence will be 1, 1, 1, then 1, 1, 0, then 1, 0, 1, 1, 0. It will be the reverse. So there, what will happen when, and toggle is a reflexive operation. So toggle from 0 to 1 is also a toggle from 1 to 0. So there, if it is a down counter, the property will be the reverse. So whenever Q0 changes from 0 to 1, Q1 will make a toggle. Similarly, when Q1 goes up from 0 to 1, Q2 will make a toggle. So what is the change that we require in this circuit to implement this? What is the change that we require? What is the change that we require? All we need to do is to replace this negative edge triggered flip-flop with a positive edge triggered flip-flop. Negative edge triggered flip-flop with a positive, because I'm looking at transitions 0 to 1, up edge transitions, leading edge transitions I'm looking at. Okay, so I would have a flip-flop which not complemented, it's not low active, it's a positive edge trigger. Okay, then I'd get a down counter. We'll soon see that actually you can convert a positive edge triggered flip-flop to a negative edge triggered flip-flop by additional gates. So we'll soon have a circuit which will change the modes of this flip-flop into a positive edge triggered to a negative edge triggered, depending on a mode input. So it's a positive edge mode or negative edge mode, depending on a mode input with some additional gate circuit. We can convert a positive edge triggered flip-flop into a negative edge triggered flip-flop. Okay, and then if we have such a additional mode circuit, you can have a mode input denoting up counter or down counter. Depending on the value of the mode input, you can either have an up count or a down count. Okay, so this is another implementation. This is slightly, I have used a JK flip-flop, but as you can see that if J and K are both 1, 1, then it's basically a toggle flip-flop. J and K are 1, 1, it's basically a toggle flip-flop. So what we have done is that we have used a JK flip-flop with J and K both tied to 1. And the first flip-flop is a negative edge triggered flip-flop with a system clock, whereas the next, second and the third flip-flops clock are the first flip-flop's output and the second flip-flop's output. Okay, any doubt regarding this? All right. So now let us see one more thing. Let us look at this timing diagram. Let's say this is my clock. So any change will happen in the negative edge of the clock. So if you observe the value of Q0, what will happen? Q0 will make a toggle here, first negative edge, make another toggle here, because it's a toggle flip-flop. This FF0 is a toggle flip-flop. Okay, so whenever a negative edge of the clock comes, Q0 toggles. So here it will toggle, toggle number 1, toggle number 2, toggle number 3, toggle number 4. This will toggle. One thing you observe, okay, now what will happen to Q1? Because for Q1, the clock is Q0. So whenever there is a negative edge of Q0, only then Q1 will toggle. So Q1 will toggle here, it will again toggle here, it will again toggle here, because at the negative edge of Q0 it will toggle, it will again toggle here. Similarly, Q2 will has Q1 as a clock. So it will toggle at the negative edge of the clock. It will toggle once here and it will toggle once here. So this will be the waveforms. Note one thing, that if we look at the frequency of the clock, and if we look at the frequency of this pulse train, you will see if the clock has a frequency f, Q0 has a frequency f by 2, Q1 has a frequency f by 4, Q2 has a frequency f by 8. Okay, so using this kind of ripple counters, you can actually reduce, you can have a clock with a reduced frequency if that is required. You can have a clock with a reduced frequency. One more thing you note is that suppose my clock looked like this. My clock looked like this with a not a square wave, with an uneven duty cycle. This is my clock. What will happen to Q0? What will happen? How will Q0 look like? So it starts with 0, then it will transition here. These are the negative edges. It will transition here. Next transition will be here. Next transition will be here. So you see, Q0 is a square wave. It has a uniform duty cycle. Sorry, it has a 5.5 duty cycle. It's a square wave. Both the on period and off period of the clock are included in the cycle of the Q0. Okay, so if we have a non-square wave clock, you can convert it into a square wave clock by using this kind of ripple counter. Okay, now as I said before, you can also have a up-down ripple counter. So you can have a mode input which will control which direction it ripples. Which direction it counts, up counts or down count. Let us look at the following. So you see that so suppose this is a mode input which can be 0, or suppose the mode is 1. Suppose the mode is 1, which denotes an up count. If the mode is 1, then what happens? This AND is a 1. 1 is a forcing input for AND, so this will always be 1. And this is 0. Sorry, 1 is not a forcing input. This will be Q0 itself. This will be Q0. If this is 1, the output of this AND gate will be Q0. If Q0 is 0, it will be 0. And this is M bar by a NOT gate. So this, if M is 1, this will be 0. 0 is a forcing gate for AND. So this will always be 0. This will always be 0. And this will be Q0. And we have an OR here. OR of 0 with Q0 is Q0. So I have Q0 here. I have Q0 here. And I have a falling edge. I have a negative edge. So this acts like a up counter as we decided earlier. And this repeats for all the subsequent flip-flops. Now if M is 0, then this is 0. This is a forcing input. So this is 0. And M bar is 1. So this is 1. So this is Q bar. This is Q0 bar. And Q0 bar and 0 is Q0 bar itself. So I am getting a Q0 bar. And the falling edge of Q0 bar, sorry, the falling edge of Q0 is actually the leading edge, the up edge of Q0 bar. The falling edge of Q0 is a up edge of Q0 bar. So this is basically, this will trigger on up edge of Q0. And if you have seen before, if you trigger on up edge on Q0, it becomes a down counter. So then this will act as a down counter. So you will get the timing diagram in the right hand side. You will get the timing diagram on the right hand side, whereas if m equal to 1, you will get the timing diagram on the left hand side. So this mode input can actually control whether it acts as an up counter or a down counter. Okay. So now these I have talked of very simple things. I have talked about mod 8 counters 0 to 7, 0, 1, 2, 3, 4 up to 7, up or down. But suppose I want, but this mod 8 is a power of 2. So mod k, if I call k, I consider a power of 2. If it's a power of 2, this way you can decide. You need more flip-flops, that's it. But suppose k is not a power of 2. For example, if k is 10, which we call a decade counter. If k is 10, that we call a decade counter, then what will happen? Then how do you design such a counter? So what we'll do, we have to choose the next upper value of 2 to the power. We have to choose so many flip-flops so that this 2 to the power n is the next upper value after k. Okay, so if k is 10, then I should choose n to be 4. Then I choose n to be 4. So I have chosen 4 flip-flops, just like the way I had done earlier. Now let us look at the transition. So I go from 0, 0, 0, 0, 0, 1 up to 10. How much is 10? 10 is 1. Oh, sorry, I need 4 values. 0, 0, 0, 0, 0, 1. 10 is how much? 10 is 8 plus 2. Up to the remaining values doesn't matter. So the remaining values are there. It should have been 11 and so on. But this we don't want. Instead, we want after this, it should go back to 0, 0, 0, 0. Okay, I'll count up to 10. Sorry, I'll count up to 9. I made a mistake again. I'll count up to 9. I'll count up to 9. And then I'll go back to 0, 0, 0. The remaining values should not appear in the state transition time. Remaining values should not appear. Okay, I go up to 9, then I go back to 0. All right, so if I call this Q3, Q2, Q1, and Q0, what does 9 means? When does 9 is on? 9 is on when Q3 is, so I can write this termination of count when Q0 is 1 and Q3 is 1. So Q0, Q3. End of Q0 and Q3. Whenever end of Q0 and Q3 is true, it should reset to 0. It should reset to 0. Okay, so how do I do that? Let's say in these flip-flops, I have a set reset unit. So this is asynchronous set reset, or maybe here synchronous set reset. So whenever it is reset is, this is an, you studied earlier, you can have an additional asynchronous preset clear input. So this is kind of a clear input. It makes it all states to 0 again. It's kind of a clear input. So what I do is, as I said, is the following. So I look at the end of Q3 and Q1. Maybe I made a mistake here. It will be Q1 and Q3. It will be Q1 and Q3. And whenever that is true, all these reset lines are set to 1. All these reset lines are set to 1. Okay, so whenever you reach a count of 0, 1, 0, 1, whenever you reach a count of 0, 1, 0, 1, everything gets reset back to 0, 0, 0, 0 by means of this reset line. Okay, so this is a decade counter. It counts up to 10. This is okay. This is a so any k which is not a power of 2 can be realized by having this additional termination circuit, additional logic termination circuit. Now let us see what happens if we cascade the counters. Because see, it's a ripple counter. So I have one counter, which is a mod K1 counter. It counts from 0 to K1 minus 1, mod K1 counter. I have the clock as input, and I have the states. Let's say some number of states, say Q3, Q2, Q1, Q0. And I have another counter, which is, let's say, mod K2 counter. Okay, it also has some states, say Q3 prime, Q2 prime, Q1 prime, Q0 prime. Okay, so if you tie up these counters, because see, nobody has stopped you. You can. What I mean by tie up is that I can. In fact, I should have drawn it the other way around. So if this one gets connected to this one, I repel further. I don't see in the repel. I was ending at here Q3. I was ending at Q2 here. I was ending at Q2. But suppose I have another block. I have another block, and this Q2 goes to the next block, Q0 of the next block. I repel further. I repel further. Okay, I repel further. So this Q3 of this goes to the Q0 of the next counter. Okay, and so basically I have a 8-bit counter now. So you can easily see if this was you can show, actually I'm not doing it. If this was a mod K1 counter, if this was a mod K2 counter, this entire thing, if we look at these states, all these 8 states in this case, will become a mod K1 K2 counter, K1 times K2 counter. They will be multiplied. Okay, they will be multiplied. Here actually what happened is that I just tied, I repelled further. I tied Q3 to Q0 bar, Q0 prime. I tied it. In general, instead of simply tying, I can have a decoder circuit here. I can have some other logic circuit here. In fact, the decoder may be a vector decoder, not just Q3. It can take all these values, and it's a vector decoder, and tie up to these inputs here. In general, that is possible. Oh, sorry. No, I made a mistake. Not like this. See, Q0 needs a clock. So what I have done here is that the output of Q3 goes as clock of Q0 bar. Goes as clock of Q0 bar. So if it's a general decoder, it will be a vector input, some kind of a multiplexer or something, and it will have a single output, and that output will act as a clock for Q0 bar. Act as a clock for Q0 bar. Okay, only in this case this mod K1 K2 happens. Even without the decoder, in the simplest form, the decoder is Q3 is the clock of Q0 bar. Then you have a K1 times K2. You can have other decoders also. So this is how it's combined. This is actually very useful. For example, I want to have a seconds counter. So I want to have a mod 60 counter. I want to have a mod 60 counter. So how do I do it? I do it by a mod 6 into mod 10 counter. So I have one decade counter for mod 10, and I have a 1/6 counter, which needs 3 bits. It's so the next higher is 8, so you will need 3 bit. So it's a 6 count, mod 6 counter. Okay, and then I tie them up. I tie them up. So it becomes a 60 counter. It becomes a seconds counter. Similarly, let's say I have a 24 counter. 24 counter. So how will I do it? I will do it, say, by 6 into 4. I can do it by 6 into 4 counter. Or I mean, for that matter, it need not be optimal. I can have 2 decade counters. So all I need is to something which is more than this 24. So I can have 1 decade counter for this and 1 decade counter for this. Okay, so it's a 100 counter, mod 100 counter, and 24 is less than mod 100. So that's also possible. There are other ways possible also. You can have smaller counters to realize this also. So in fact, for this matter, if I had a 8 cross 10 counter, that is also suffice with additional circuit to make mod 60 counter. All right. So this is how this can be easily designed. You just have to. So there are two basic things. One is how you make it a up counter or a down counter. Second is how you have a K, which is not 2 to the power n counter. You have an additional NAND kind of circuit, AND kind of circuit to terminate at the highest count level. And then in general, you may also need a decoder, because I'm counting 0001 like this. I may need to have other definition of states in the other counter, second counter. They may have different assignment states. So I need a converter. I need a decoder to convert the state assignment from the first counter to the second counter. Okay. For example, if it is a decade counter, I'll need 4 bits. If it is a 6 counter, I'll need only 3 bits. So you can do something also. Just one more small thing that problem may happen in real life implementation of this ripple counter is something known as a glitch. A glitch is a temporary undesired states that come up due to delays in the gate circuit and the flip-flop circuit. They arise due to delays. So the phenomena is like this. So suppose this is my counter, and ideally it should count like this. Ideally it should count like this. So if you look at the clock cycles, this is clock cycle 1, this is clock cycle 2, this is clock cycle 3rd clock cycle, and so on. It should happen like. But what may happen, and these changes will happen at the edges of the clock. Okay, at the edges of the clock. What may happen temporarily, we'll see how it will happen. Temporarily, I may have some undesired states for a small amount of time. This should go to this, but in the next clock cycle at least. But for a small period of time at the start of the clock cycle, there are two intermediate states that are observed. And they go away, they are temporary, they go away after some time. We'll see how they are observed. But sometimes these glitches may create a problem, because if you are actually probing the output at exactly this interval, you will see a wrong output. If you are probing Q1, Q2, Q0, you will see a wrong output here. Okay, let's see how it happens. So this is a typical falling edge diagram. So ideally, what should happen when the clock falls? This is the clock. When the clock falls, let's say this call is a Q0, Q1, Q2, and immediately the falling edge, this should toggle. But what happens actually is that there is a small delay. Similarly here, there is a small delay. Similarly here, when Q1 toggles, again there is a small delay because of the gate delays. These delays are basically due to the capacitance in the circuit, RC delays, resistance capacitance delays. Similarly, this is the circuit. All right. So in the middle of this clock cycle, what is the value? 1. Here the value was 0, 0, 0. All 3 are low. Here the value is 1, 0, 0. That's the correct transition, maybe from 0, 0, 0 to 1, 0, 0. But let's see what happens in this small interval. So what happens here is this here, for the small amount of time, it should have been, it should have been 1, 0, 0 right from here. But in this small interval, it is 0, 0, 0 still. It is still 0, 0, 0. Similarly here, it should have been 0, 1, 0. But in this small interval, it is 0, 0, and 0. Okay, so this 0, 0, 0 here should not have been there. It should have been 0, 1, 0. Similarly, the 0, 0 here should not have been there. They go away after this delay. They go away, but temporarily they are glitches. They are undesired states. Okay, so these glitches will always happen in ripple counter. We'll see how you can use synchronous counters to remove these glitches. Okay, that we'll do in the next class. Thank you. Any question?